Thanks all for coming. I didn't actually collaborate with the earlier speakers, but I'm going to endorse basically everything they said. Raluca's, the adoption, Mike's, everything. The promise of confidential computing is that everything that affects your security should be visible to you. You should see the code. You should manage the rules, all of that. And then finally, it's a slightly abstract point, but the point Microsoft makes, there's no such thing as zero trust unless you verify the measurement of the thing you're talking to. Software always mediates interactions. So without that, there's no such thing as zero trust. I want to overcome the barriers. So the one thing I don't disagree with, Raluca, is I don't want to wait till 2028. I want the version of confidential computing that people can use in a program immediately, like 15 minutes. Sort of Linux. I was at Bell Labs during the Linux days, and I thought that was an exciting opportunity. I'm going to talk about confidential computing a little bit more technically. What I mean by confidential computing is any platform, a washing machine, that has these properties. It can isolate a program, it can measure it, so it has a unique, universal, unforgeable identity. It can store secrets for that program, and it can do attestation. Whit Diffie once accused me of inventing the name attestation. I don't think it's true, but it's a little bit gotten out of control. So isolation and measurement is, you load a program into the thing, you measure it, take a hash, for example. That's its identity. That program can ask a hardware platform to store the secrets for it, identified by its identity, and then get those secrets back. That's very important for cold start without going to an attestation or a verification service again. And then attestation. This is the way you establish trust between programs. So, but in a summary, what confidential computing really gives you is protection against malware, insiders, and complete auditability of everything you run. I think actually they had much better graphics. The earlier speakers talked a lot about the applications, and I agree with all of them. Just standard dopey, make your applications more secure. Safe program execution, zero trust. Collaborative machine learning, data sharing. You'll see, apparently we all have demos about collaborative machine learning. You'll see one at our booth. Secure motion planning. If you're iRobot and you, right now, your robot wanders around the house and they send data about your house to the thing and it does motion planning and all that, it's like, well, I'm not sure I want iRobot to know everything about my house. With something like confidential computing, they can do that and never see your house data. If you're Intel and you're using somebody's tool, they can service it the same way. Container management, which is mentioned, secured document sharing among different organizations. One important one coming up is edge collection. So if you're doing an AI system, or basically any system where there's lots of sensors, you want to guarantee the integrity and often the confidentiality of that sensor data from the start, from the beginning. This is increasingly important in the age of disinformation. So there are many applications. In fact, again, probably this is not what the marketing people teach you. It's like I can put up a slide and just say everything here is what you should use confidential computing for. I stole this, I think somebody in the room, actually, I read this on the thing, but several people have said it. In the future, there's no reason for any program upon whose security you rely not to be a confidential computing program. So the question we asked ourselves is, geez, why isn't everybody using it? And there are a few questions, there are a few answers. One is T availability. It's not every computer doesn't have these. Eventually, we like to see it even on clients. The programs, if you program for SGX, you have to do something to it to make it run on SEV or an ARM platform or Keystone. And that's a barrier, unlike Linux. If you write a Linux program, basically you just recompile it. Everything works fine. Software, writing a program from scratch is actually a fair amount of work, and you can mess up the security. And you can make subtle mistakes. For example, if your application is verifying rules, it's often not portable because it needs to know all the other measurements of all the other programs it's ever going to talk to. So there are lots of scalability and management problems you can get wrong. And often in many of these systems, the policy is hard to understand. I wanted so that when you write a program, you're not at all unsure what your security policy is, your trust policy. So the question is, what's the Linux for confidential computing? That's the question we set out to answer. We've been working on this a while. We've used some of the SDKs. Here's a long list of all the things you have to do right to write a confidential computing program. And we didn't want most users to do that, or even most smart programmers. What we wanted is, here are the instructions, write a program. Did you write it right? Did it do what you wanted to have the security properties you had? We have used earlier SDKs, which were very helpful. They were mostly focused on making SGX programming, which had a fairly difficult programming model, easier to use. And in particular, Grameen, which kind of makes programs fairly portable. But it was still too much work. We ourselves sat there and said, I don't want to write a program. There's a barrier to actually writing a confidential computing enabled program. And I think that's like a major mortal sin. So we wrote this open source, wherever Mike is, framework for confidential computing, and we'll take him up on his offer to have it in the CCC. We found it vastly decreases time to write applications. We've had people literally take an application and modify it to use this framework in 15 minutes. And honest to God, that's the goal. We don't want the vast majority of people with relatively simple security models to take any time at all to build their application, or hardly any time at all. We wanted to avoid the platform portability problem. So we support SGX via Open Enclaves and Grameen, AMP, SEV, SNP, ARM. Samsung has contributed ARM support, RISC-V Keystone support, which UC Berkeley has contributed. The API, we think, is like super duper simple for almost all cases. And you can see that in the technical talk. But if you have a complicated case, there's support for those too. So we do that. Very simple management. And it's all embarrassingly parallel. If you want another 9 on reliability of getting to your certification, we call it certification rather than attestation because it evaluates all policy. You just add more servers. They're all, things are not available when you can't get to a server that can validate this. We also arranged it, and this was important to some of the hyperscalers. There are no deployment changes if you use a cloud service. And in fact, we want our things to work whether you're in the cloud, whether you're at home, whether you're at your desk. It should not be dependent on other infrastructure. Should be able to use it, but not dependent necessarily on it. As everybody said, we want auditable, comprehensive policy. In fact, when we certify something, when we say this program should be trusted, you get an English language, people might accuse me of not being English language, but a nearly English language proof of why you should trust that program. And we wanted it to be very efficient to add new components. So you don't have to say, oh, sorry, that old version of the program is not going to work anymore because we added something to our, we call it a security domain of trusted programs. And we, most importantly, at least for the marketing guys, we wanted to enable all the new services that people have talked about: data economy, data sharing, high security applications, regulatory requirements, all that. But my secret thing is the thing I told you already. So the secret's out. If you want to write a secure program, you should be using confidential computing, period. The framework consists of 2 parts: a certifier library which is the interface to all these primitives that front ends all these platforms. There's a lot of stuff in that box. It's literally, you can come to the thing, 3 basic calls to stick in almost all programs to make this work. And then there's something called a certifier service, not an attestation service, which validates the policy in the domain and sends an X509 certificate to the application. After that, the application doesn't need to know anything about the confidential computing primitives. It talks to other components using that. The certifier service, we can check everything, the attestations and everything. And generally, we recommend that. I think the Microsoft person said, any user should be able to check everything. We agree. But if you want to use an external platform attestation service, you can do that. We support all these platforms. One thing I mentioned that the Microsoft mentioned the distinction between application-level enclaves like SGX and secure encrypted virtual machine enclaves like AMD SEV. We actually have a primitive, so if you have a secure encrypted virtual machine, not only can you protect the virtual machine, but that virtual machine can provide the confidential computing primitives to each individual application. So each individual application can have the restricted TCB of an SGX application, but they're much easier to write because the API they're talking to is Linux, not a limited one. The service runs anywhere. Literally, you could run it under your desk. And most of the time, your low-powered machine under your desk actually can service a pretty big network of confidential computing programs. But you do want to make sure of availability. So you can have many copies of that and get high availability. So the service runs anywhere. You can have somebody run the service for you. Again, my prejudice is the whole idea of confidential computing was make sure I was in the driver's seat. Why do I want to say, okay, why don't you drive my car now? So I typically want to do it myself. But you could have a service, you could have one of the cloud providers do it. You could use an external service, whatever you want. This supports that. Again, all of it's open source, both the client side and the applications and the service side. Yeah, so it runs everywhere. And in fact, in our demo, you'll see apparently the same demo everybody else has done with a model. We train a model somewhere and we make the model available somewhere else and somebody consumes it somewhere else. In our example, however, the model is trained in a Grameen SGX enclave. It's made available in an SEV machine enclave, and it's consumed by an ARM or Keystone client. So it's protected end to end. And literally, that was the use case we wanted. The person who did that in less than a day on all the platforms. And that's really the honest-to-God goal of this. So if you come to the technical talk, you'll see the one slide with the here's everything you have to do. We have a community. We've had this in open source for a while. It's now pretty close to being, the base case is being baked. It's actually, I say it was baked. And we've had contributions from important contributors like Samsung and AMD and Berkeley. So we appreciate that, and we welcome others to join or use whatever you want. It's Apache licensed. But really the key thing, and I don't think this is a source of departure from Raluca, but I actually am more strident about it, is I want to make confidential computing a universal platform. I don't want people to worry about their 16 platforms. I don't know which one to use. I don't know which one to buy. I don't think that should be a barrier. And I sure don't think programming them should be a barrier. So I think the key message probably throughout this is make it universal. Now's the time. There's no reason for you not to use confidential computing now. And there are many use cases for which there are no other solutions that are efficient. As Raluca said, if you use fully homomorphic encryption, that's a great idea. You have to program things special. It takes a long time and may not be that efficient. I'll close. I actually done several of these systems, one at Berkeley when I was there and at Google. The tagline is your stuff's safe everywhere. David Wagner suggested this, and you can tell me whether this was a good idea. I said, before confidential computing, you have to write an application correctly to make it secure. And you have to do all this other stuff to provision the application in the cloud or wherever, even at home. And basically, there's no way to check that that's right. So before confidential computing, there was no way to do this. You could go to your worst enemy and say, trust me. With confidential computing, you could do it, but the normal way to do it was that you'd write applications for every back end. You had to manage migration yourself, implement all the crypto, do all this stuff and make sure it was scalable. And then you had to implement a trust policy, which confused almost everybody. So the middle column is, once the hardware is available, you could do it, but it was awful hard. We'd like to think with the certifier, you still have to write the application correctly. But using the API and the trust policy tools, it's really easy to get the thing working really in a short amount of time. And that's really the barrier I've experienced with software adoption for most things. If you can't cut and paste an example and put your application in, at least in the beginning, people just don't have the patience to do it. So you don't have to be too patient with us. You have to do that. So come to the booth. You'll see a very similar demo to the ones you've seen today. And we'll answer any questions you want. So thank you.